Hi, welcome to the Signal Pad. In this episode, I have another product review for you guys. Today, we'll be taking a look at this Rohde Schwarz ZNLE6 2-port 6 GHz network analyzer. This is a fairly new instrument from Rohde Schwarz and is part of their economy series instruments that they've been releasing across a wide range of applications. Now, I'm happy to see that Rohde Schwarz strategy appears to be, instead of cutting costs, is to add features at the same price point to stay competitive with other vendors like Keysight and Anritsu and Tektronix and so on. So it's good to see that instead of trying to go the route of we will give you the cheapest price, they will give you the highest number of features. And I think that's a really good thing for consumers. And of course, you get all the advanced features and reliability and the build quality and the support of Rohde Schwarz. And I'm happy to see that them pushing so aggressively in this price point, because it obviously, as consumers, then we will benefit from that. So we'll take a look at extensively how well it behaves in terms of its dynamic range, performance, GUI, and we'll take it apart quickly just to take a look and see what's going on inside it. It's going to be a long video. There's a lot to show you, so I hope that you enjoy it. Let's get started. Now, as you know, Rohde Schwarz has a wide range of network analyzers, and they're among the best in the industry. And their network analyzers can measure up to 0.5 terahertz and up to 48 ports. Of course, not 48 ports at 0.5 terahertz. I don't think there's anybody who needs 48 ports at 0.5 terahertz. And if you do, send me a message and I will send you a basket of cookies. But having said that, they're categorized into high-end, mid-range, and economy categories. Now, we're not going to look at the high-end and mid-range. It's just going to make us jealous. Let's just jump directly to the economy. So the ZNLE is the second model in this series. The ZNL is essentially the same as ZNLE with some additional functions, including a built-in spectrum analyzer. So this itself is also a very nice unit. So we're going to take a look in detail to the ZNLE. As you can see, two models are available, one up to 3 GHz and one up to 6 GHz. In terms of specification, they're very similar, the ZNL and the ZNLE. It's just that the ZNL has a few more functions built into it. And if you go down, there's some portable ones as well. And in these portable handheld models, I already reviewed the portable spectrum analyzer, which was also a very nice unit. So take a look at that if you haven't seen it. So now I'm eager to take a look and see how this behaves, do some experiments with it, and see if it's worth the price. And here's the front panel of the Rohde Schwarz ZNLE6, and as you can see, it uses the new modern look and feel of the Rohde Schwarz instruments, and it has the same 10.1-inch WXGA resolution LCD screen. Still is very shiny and reflective, but you can get an anti-reflective layer that you can put on the screen yourself. I actually had one, but for the life of me, I couldn't get it on without getting bubbles underneath it. So I eventually just decided to give up and use it as it is. It's not too bad if it is in a properly lit environment. It can, some angles, again, it can be a little bit annoying, but it is a very nice LCD screen, high resolution, multi-touch, capacitive, responsive, just like it was on the oscilloscopes. On the left side, we have a couple of the primary buttons typically used for dealing with utilities and setups and presetting the instrument. Keyboard button, thank goodness that it is there. This is very handy, especially if you don't have a mouse and a keyboard. And two USB ports, and of course a recessed soft power button. On the right side, we have our RF ports, RF port 1 and RF port 2. This is a full S-parameter instrument, so you expect to have 2 ports on there. These things can take 27 dBm of power and 30 volts. So if you're using this to measure an active amplifier, as long as it's below a watt of power, you should be okay, but otherwise you would need an attenuator. The keyboard, nice and large, with the units being a different color, directional pads, and of course the rotational key. Very nice and simple and intuitive interface. I haven't really had any problems with it. And everything you would need to access on the top here, every particular settings of the instrument are all handled there. We'll take a look at it carefully once we're going through it. It does have the front bumpers, which extend beyond the surface of the instrument. These are critical, especially for RF equipment, in case they fall or in case you need to rest them on the front. They extend beyond the RF connectors, the screen and the knob, so that it would protect them. This is great. And this also is used to mount the front cover in case you need to transport the unit. The front cover is a little bit difficult to get off. On and off the unit, but I would imagine that you don't have to do that all the time. As you can see, it's a pretty nice and small and compact unit, and this is one of its main selling features. It is such a nice unit to be able to have on your bench, and we'll talk a little bit about that as we're doing some testing. Now, the depth of the unit is only 9.4 inches, and if you've ever used a network analyzer on your bench, you would appreciate a low profile one. And the reason is because once you have the unit calibrated and the cables coming from the front panel, you don't want to have to move the cables a lot, which means you would want to have this at the back of the desk sitting in front of you. And the least you need to move it around, the more space you have in front of it, the better it is. And this is why they have spent so much time making sure the depth of the unit is manageable. And this is going to be very handy once we do our calibration and our measurements here as well. So let's take a look and see what's at the back of the unit. And here is the back of the unit, and it uses the same structure as almost every Rohde Schwarz instruments, with multiple sections that can be taken off for various cards to be put in and out, like power supply, main motherboard, and so on. This is a very interesting and useful architecture where things can be inserted at the back of the unit as opposed to having to open it and remove it from the inside. So having said that, given that this is running a full Windows machine, Windows 10, and it therefore is fairly straightforward to add various ports to it, and it takes advantage of that, gives you a DVI port, gives you a LAN, of course, and two USB 3.0s at the back, which would be used for what you would expect them, electric compatibility, fast data transfer, and getting an external monitor. The power supply over here, as you can see, has a hard switch as well. It is nice to have this at the back of the unit. Sometimes you want to completely cut it off from the line, and this is what you can do with this. There's a lock location here to lock it onto a bench. Given that this is also targeted a lot for educational purposes, it's nice to see that you can lock them in the lab and keep them safe from being accidentally moved or taken out of the lab. Here's a GPIB port at the top. This is an option. You don't necessarily have to have it, but it's nice that you can get it, especially for legacy support, and reference in, reference out, and trigger in. BNCs are also accessible at the back, which we will use in some of our experiments. So the unit is really quite straightforward, very easy to use and easy to understand. So now the question is, how does it perform? What does the GUI look like, and what kind of experiments we can do with it? And that's where the fun part starts. Let's go. I also wanted to quickly show you what the inside of the unit looks like. The Rohde Schwarz instruments are really quite nicely engineered on the inside as they're on the outside. This is not going to be a detailed teardown. I'm going to leave that for some other time, but this will give us an overall architectural view. So there's a main motherboard here at the bottom where all the different functions and cards are plugged into. So this is the main RF deck. And you can see there's two ports that are connected to it. One is coming from the top. You can't see the top of it from this angle, but these two ports could directly go into there. Interesting to see an unused SMA connector there. I wonder if this is used for the ZNL model with the additional functionality. There's also a card that's not populated here, and I wonder what they're doing with that. Maybe a digital IF section. I'm not sure, and this could be some kind of an LO signal that goes between the two, or maybe an IF signal. So having said that, you can see that these two coax cables cross each other on a 90-degree angle, most likely on purpose to reduce EM coupling to each other, because the magnetic fields will be perpendicular. So this is needed perhaps for a dynamic range that this instrument needs to have. Now if I were to rotate this a little bit, you can get a better idea of the thermal planning they've done. Air blowing across all the cards, very nice, very clean design. All the connections to the front, keypad, and LCD screen is handled over there. I can go ahead and rotate this further, and we can see inside the unit with all the different cards that are there. And from the other side, you can get some more look at the design of the power supply. Again, very nice. Everything is just beautifully done here. There's some connection on the other side, which is also interesting. Perhaps this motherboard can fit in a different way where some other card can be plugged on the other side, some more empty slots. This, what you see here, is the GPIB. There's a similar card on the other side. That card plugs also in, which is the reference in, reference out, and trigger. And it looks like it has a can around it. I wonder if the reference is entirely built onto that board and then fed onto the main motherboard. You can't see the processor from here, but there is some hint of some of its locations. Let me rotate this a little bit more. Again, the power supply, nice and small and isolated. On this side, you can see this card over here has all the display port and USB and LAN on it. There appears to be a big part over here. You can see the back of the BGA, and that is likely either an FPGA or the main processor. Just look at how beautiful it is. Really, it's just so nicely engineered, and you can see the difference in the material between this PCB and this PCB. This, of course, being a millimeter wave, or I shouldn't say millimeter wave, this is a microwave PCB. I work in millimeter wave, so I tend to say that a lot. And but this difference in dielectric material, this could be FR4 or some other type of PCB. So yeah, very interesting, nice and compact design. I think as always, the Germans, engineers, and Rohde Schwarz in general, they really know how to design this. So very nice. Let's go and see how it performs. One other little point, even the power supply is made in Germany. No expense spared here. It really is quality instrument. A good place to start using the instrument is, of course, to calibrate it. Now, you can calibrate the network analyzer using a calibration kit if you have one, or you can use a Rohde Schwarz calibration unit. This is an automatic calibration unit. This particular one is the ZNZ151, and it goes from 100 kHz to 8.5 GHz. This is a 2-port SMA calibration kit with a USB connection directly to the instrument. Now, as soon as you connect this to the unit, The unit will download all the calibration coefficients, is aware of exactly which model you're using, and takes all the data, downloads it into the unit, and when you do a calibration, it will take all of that into account. This is similar to, let's say, the Keysight's eCal modules, works in a similar way. It's exceptionally fast and very reliable. Now, the ZN15 series has really a wide range of automatic calibration units. There is one version that goes up to 67 gigahertz, which will of course use V connectors. There's also all the way to 21 ports, so you can do a 21 port calibration. Even a 24 port calibration of this particular series exists. Now, a 24 port calibration module like that is used for backplane designers that have many parallel channels and want to see reflection coefficients and crosstalk across all of their channels, looking at every possible combination of S parameters. Now, we don't need a 24-port calibration module. A 2-port would be just fine, so I'm quite happy to have this one. And the specification of this one exceeds that of this instrument. It goes all the way to 8.5 gigahertz. We don't need that. This one we only need 6 gigahertz. And this starts at 100 kilohertz, which is nice for some of the instruments that do support that. The ZNLE6 starts at 1 megahertz. So it's really sitting comfortably within the range of that. So I'm going to go ahead now, focus on the screen and show you how that works out. A couple of other things to note is that I'm using fairly high quality SMA cables here with a Type N to SMA converter directly sitting at the output of the unit. Now, the reason I'm not using a very high-end cable at the moment is because for our initial experiments, we don't really care too much about phase stability, and we're not pushing the dynamic range of the instrument. Towards the end, when I'm going to be doing that, we'll switch to, of course, the best in the market, pretty much. These are Gore cables, and I have one starting from Type N at one beginning and SMA at the other end. These are very expensive, high-quality cables, and Rohde Schwarz deserves to be used with these in order to get the best dynamic range and phase stability from the unit. But for now, we'll be just fine with the cables we're using. So let's take a look at the screen and see what the calibration looks like. So let's take a look at the GUI here. Now, for most of the video, I'm going to be using a mouse simply because I don't want to bring my hand in front of the screen all the time to touch it. I have no problem with the touch screen. It's fast, responsive. It works just as well as any of the other instruments. One of the only complaints I have is that some of the buttons on the left here are a little bit too small. It'd be nice if they were resizable, so when you're using the touch screen, you could make them a little bit larger, as you can see, compared to the size of my finger there. But they're still quite usable. You can still touch them if you have small fingers. All the other buttons for all the other settings are perfectly sized. I have no complaints about them, and they work really well. So let's do it as primary calibration. Now, this instrument actually has a wizard built into it, and the wizard will walk you through the S-parameter setting of the instrument as well as the calibration. Now, engineers typically don't like wizards because they want to set everything up themselves, but it is very useful in an educational environment or if you're new to the instrument. So let's go ahead and give it a try. So I'm going to press measure here, and I'm going to use the S-parameter wizard. So it's going to now walk us through that, and it's showing a picture of a much higher end network analyzer just to make us jealous, but we're going to skip this step. Go next there. So now it tells us, how do you want to set up the instrument? Do you want to do a single-ended 2-port measurement or a balanced 1-port measurement? This is great because we can actually do a balanced measurement later on. For now, I want to get a full S-parameter at 2-port, so we're going to choose the first one. That's fine. And next, and here we can set up the system impedance and the logical order of the ports of the VNA. Now, most of the time, logical port 1 is port 1 and logical 2 is port 2, so I'm not going to change that. The system impedance is 50 ohms, but you could change it and put it anywhere on the Smith chart, which is nice. And for a theory of operation, we're going to use traveling wave, which is a default. It's fine. I'm not going to talk about power waves. We can worry about that later. So let's go next here. Now, how do we want the results to be displayed? Well, I really like this particular setup. This is what I use most of the time, where S11 and S22 are shown on the Smith chart, and S21 and S11 are magnitude responses in this nice quadrant view that you see. So we're going to stick with that. And we go next. Here's the frequency of operation. Let's do a full band measurement here. So from 1 megahertz to 6 gigahertz. And the number of points is 201. I'm going to change that to 501 just so that we can get a little bit more spectral resolution here so that we can see small changes in the frequency response, because I'm going to be measuring a very high quality factor microwave filter, and we can benefit from that. So let's go ahead next once again. And here we can set the IF bandwidth of the instrument. Now, if you set a very large IF bandwidth, the instrument will be very fast, but it will not have as much dynamic range. If you do a very fine IF bandwidth, the instrument will slow down significantly because it needs to gather more energy in order to compute the S parameters, but at the same time, it will have a much higher dynamic range because the IF bandwidth is so much smaller. So let's go ahead and choose a medium speed here because it would allow us to have a good balance, especially because we're measuring again, as I said, a high quality factor microwave filter. Now, this is a passive device, so I'm going to have the incident power at 0 dBm, which is set over here. It'd be nice if this instrument actually had 10 dBm output power, because for some of the very lossy systems, 10 dBm would be useful, or for some very far crosstalks, higher power would be good so that you'll be within the dynamic range of the instrument, but it goes only to 0 dBm, so we're going to do the maximum we can. And we go next over here. So now we're done with setting up the instrument. Now it's asking us, do you want to calibrate or you want to skip that? Well, obviously I want to do a calibration, and we're going to do an automatic calibration because we have an auto cal already connected to it. Let's go finish over here. Now we're going to get the menu for the automatic calibration. Now here we have the cal unit detected. Characterization, we're going to use the factory, which is a female SMA on both terminals of the calibration unit, and that's exactly what we have. And it's going to use a calibration type UOSM. Now UOSM is a Rohde Schwarz terminology. A U is an unknown through length. There's a whole theory behind how to do S-parameters with this. There's a paper associated with that. I'm not going to go into the details of that, but U is for an unknown through, O is open, short, and M for match. So that's a full characterization, so we're going to keep that. We're going to go next, and it also asks us what is connected to what. Is port 1 connected to port 1 of the calibration unit? And that's exactly how I have it, so we won't touch any of that. Now we go start, and it's going to do a calibration. You can see how that looks like. There it is. You can see exactly what it's doing. It's going to do an incident power. Let me do a full cal sweep there. There you go. So now it's going to do an incident power on the left. It does the calibration on that port, and it measures all the different combinations in order to have the response of it. So we're going to wait for it to go through. There you go. Now it's doing port 2. And once that is done, it should be all finished, and it's going to give us a fully calibrated instrument back. And again, remember I set the IF bandwidth to a much smaller value, so it takes longer obviously to go through it, and we're happy with this, so we're going to apply that. And there it is. We are now calibrated. Now the impedance of the cal unit is not known, so you can't rely on this measurement to judge whether your calibration was good or not. That's just because there is a droop here doesn't mean that the calibration wasn't good. So now we are fully calibrated. We can actually go ahead and start doing some measurement. So let's do something very basic just to make sure our calibration even makes sense. Let's connect a 50 ohm termination onto it just to see what happens, and then we will measure our filter. So here I have disconnected port 1. You can see it's disconnected, and you can see the S parameter S11 directly on the outside of the Smith chart there. So I'm going to terminate it into a termination from my calibration kit just to show you that indeed we do have a calibration that we can observe on the Smith chart. There it is, bring us back to the center of the Smith chart. Now this doesn't tell us exactly the quality of the calibration, but at least we know that we are close to the 50 ohm point there. So now I'm going to go ahead and connect it to my cavity filter, which is adjustable, and then we can do some detailed measurement on that. As you can see, this is a Wavetech tunable bandpass filter, and it can go from 1 GHz all the way to 2 GHz. I will also be curious to see what happens beyond the range it is which is specified for, and see if the performance really degrades all that much outside of that range. So I'm going to get this out of the way so we can look directly at the screen and see what happens as I tune it and what kind of performance we can expect from such a cavity filter. So let's look at the filter response here. We can see all the S parameters. Now S11 and S22, which are on the Smith chart, are going to look quite messy, that we're looking at a full range well beyond the bandwidth of this particular filter. S12 and S21 are symmetric as they should be. This is a reciprocal structure, and we can see the peak of S21 and S12, which is the bandpass response of the filter, exactly where it is mechanically set to. So let's go ahead and maximize one of these so we can see the waveform much more clearly. And here you can see much better the peak of the filter. So let's get the marker on there. Let's move the marker close to where our peak is, and there's acceleration built into moving the cursor with my mouse, which is quite nice. There you go. We see 1 GHz. That's where the peak is. That's exactly where I have set the filter to. So that makes sense. Another interesting thing to note is that the filter has higher modes, which are undesired, but they are present because of the fact that this particular structure of the filter is going to have other modes. Now they're quite a bit lower. There's about 30-35 dB lower than the fundamental, but we will see that they do indeed move around as I change them. So here we go. Here we're looking at around 5.2 GHz. We see indeed another response. Now, because I'm looking, even though I'm looking only at this frame, only at S21, I still have full sweep on all the 2 ports. So on one sweep, you can see the waveform being updated, and the second sweep, the power is applied on the opposite port, and the other S parameters are being updated. That's why you see 2 sweeps that are updating the waveform at the same time. That's normal because we have all of the S parameters active. So let's go back over here, and there's a filter there. Now, if I want to move the waveform up and down, it actually has a very nice graphics associated with it. So you can move it up and down there, and it latches onto 10 dB divisions at a time. It's very intuitive. I really like this little animation. Simple things like this really make a big difference. So if I move it all the way up and put the reference at -30, you can see that the noise floor and the floor of the response to the filter is sitting at around -110 dB. That's a huge dynamic range, and we're not at the highest dynamic range. We're not at the lowest IF bandwidth anyway. So let's go ahead and put this back onto our 0 dB reference there. So there's our marker at the peak there. I can go ahead and take a closer look at it by zooming around this little area. There we go. You can see the filter shape and the band pass of the filter, and we're going to take a closer look at that too. If you see these little edges, the reason is because we don't have enough points to cover that part of the curve very smoothly. We have 501 points across the entire bandwidth, so we have discrete points here, which it is doing 0 order holds or second order holds in between them. So that all makes sense. Okay, let's go back, zoom out there, and we can use some built-in functions to actually calculate the property of this filter, which is quite nice. So let's look at some of the marker functions. So under the marker menu is where, of course, you can define all the different markers you can have. But under the marker search functions itself, you can define a whole bunch of different parameters for the instrument to help you find various peaks, minimums, and maximums. Especially if you have multiple peaks, like in this case, we can click on that and we will get all the different peaks associated with this filter response. So we can see everywhere where we have various cavities and various resonances and band passes that are undesired are labeled quite nicely. So we can use this function, of course, and let's go ahead and turn all of this off because that's not what I really wanted to do. What I wanted to do is to measure the filter response. So if you go on the band filter, it has a built-in function to detect the filter response. Now I'm interested in seeing the 3 dB band filter, so let's go ahead and use that and click on that, and we will get now detecting exactly where the filter's major bandpass response is and all the associated characteristics of that. So we can take a look and see if this actually makes sense. First, let's zoom in around the area where the markers are placed so we can see if this makes sense also. And we can see it has detected marker 1 and marker 4 as the primary bandpass response to the filter, and marker 2 and marker 3 are 3 dB down. And it has labeled all of them with their corresponding frequencies here on the right. So we can see the center frequency of the filter is roughly around 1 gigahertz. We knew that from before. And we can see also the bandwidth of the filter is about 42 megahertz. That's the bandpass filter at 1 gigahertz. And the number also makes sense. And the lower and upper edges are also labeled. So the quality factor of the filter, given its center frequency and bandwidth and the drop-off ratio and all that, is a factor of 23.6 and a loss of 1.3 dB. So we have essentially all the important characteristics of this filter being done automatically by the instrument. So let's zoom back out and let's go ahead and change the frequency response by changing the filter center frequency. So right now we're at 1 gigahertz. Let's go ahead and move it to 1.5 gigahertz and see what happens. There we go. Now I've set it to roughly 1.5 gigahertz, and you can see the screen, of course, updates accordingly. Now if I go ahead and zoom in again around this point here, we can see that similarly the filter response has been detected. But it's interesting to note that the bandwidth of the filter is now 67 megahertz, and that makes sense because the fractional bandwidth of the filter hasn't changed, but the center frequency has moved up, and that is also corresponding to normally how filters behave. It's much easier to get a larger bandwidth at higher frequencies than it is at lower frequencies because your fractional bandwidth has to stay the same. So the quality factor of this filter is about 23.3, and the loss is less. So this filter is tuned for lower insertion loss at higher frequencies, and we can see if this trend continues. Let's go ahead and try it again. Now let's take it to the maximum of this filter's rated 2 gigahertz. Here we go. That's 2 gigahertz. And we can see again that the filter response has moved forward. Now our bandwidth is 96 megahertz. Is even more, so about twice as much as it was before, which makes perfect sense again. Quality factor is about 20. Insertion loss is 0.8, so it has better insertion loss. Now we can also see that the other modes of the filter are really, really creeping up now. So if I were to go ahead and add another marker to the filter, let's go ahead and add a marker, this time marker number 5, and let's move that marker to somewhere where we would want it to be. So let's say I can just drag it right around here, so around 4.1 gigahertz. We have a fairly strong bandpass filter response again. It's only minus 15.9 dB down. Considering that the center frequency loss is minus 0.8, this is only a 15 dB rejection, so this filter doesn't work very well at these higher frequencies. Now what happens if you try and take it beyond what it is rated for? Is it still going to operate properly? Well, let's try it out. I'm going to go ahead and increase it beyond where it is rated as. And we can take it all the way over here. And now let's take a look at this. Now it looks like it is working, but if you actually go ahead and zoom in, you'll see that the response is quite bad. Over here, you can see that we do have 2 peaks and we do have a major drop here. So even though the marker's 3 dB points are still within its primary peak, the other peak is even higher than the 3 dB point down. So this is not a very good response anymore. You can see it's quite asymmetric. The quality factor of the filter would be quite poor if you take into account really how wide it is and how the drop rate is. So it's definitely not intended to be used outside of its frequency of operation. But very quickly, you can appreciate how easy it is for this instrument to really capture the behavior of the filter, all with built-in functions. So let's go ahead and get rid of some of these measurements. So I can go ahead and go all markers off, but then it doesn't really get rid of this. There's a bit of an unusual bug here because I can't right-click on this anymore. So I have no way of getting rid of this. And the only way I found that it works is if you go under marker, create a marker, all of them off again, then you go back to this one, and then go back to the main screen, and then you go all markers off. I think that's how I managed to get rid of it last time. And then this button doesn't quite work, this X. There's a few little tiny bugs in there. Let me see if I go under marker again, and I go all off. There you go, now it gets rid of them. So there's a bit of a weird issue going on with that. And this X doesn't work all the time, which is a little confusing. And I think it doesn't work when it's intended to automatically go away after about 5 seconds. But then if I want to disable that, it keeps coming back. There's a bit of weird GUI issues in there that I'm hoping that they would fix. So let's go ahead and go back to all of our diagrams here. So let's take a look at S11. But let me go ahead and maximize S11 here. So let's go and change it from Smith chart to a dB so that we can actually make sense of it, given that it is such a broad bandwidth. We can go ahead and change the format. There are many ways to do it, but you can just press the format button over here, and instead of Smith chart, you can just go on dB. There it is. So now we can go and auto scale it. Here we go. Auto scaling can be done just by using the scale button. I was trying to figure out how to do it with the mouse, but it's fine to do it with that button as well. So there we go. We can see over here, double clicking here and get a marker. So this is now a real center frequency. Now we are beyond the frequency in which the filter is supposed to operate. So let me bring it back to around the middle of its range. Let's say put it at 1.5 gigahertz. And you can see at 1.5 gigahertz that it does fairly well. Let's go ahead and zoom around here. There it is. So you can see it does indeed drop quite a bit. It hits minus 24 dB, and it is below minus 10 dB for the range in which you're interested in to operating the filter. So it works reasonably well. And I can go ahead again and change the center frequency around, and you can see, for example, at 2 gigahertz, which is also within the frequency response, we get a very, very good return loss. In fact, it's probably the best around this frequency. And I go and zoom around here, very, very nice. You can see it's minus 23 dB, so it's going to have very good voltage standing wave ratio. So I'm quite happy with the response of this filter. Now there's one other thing I want to show you. The speed in which it sweeps may be a little bit misleading because you may think the instrument is slow, but let me reconfigure it to only sweep one parameter and increase the IF bandwidth to see how fast it actually operates. So here's the instrument with the same number of points, 501 points. The IF bandwidth is now 10 kilohertz, and I'm only showing S21 on this channel, so therefore we're not sweeping the other parameters. And look how fast it is. I can go ahead and move the filter, and check it out. You can see how quick and responsive it is. I mean, it's essentially instantaneous as far as we're concerned. So it's excellent for doing something where you need to track in real time and make sure that your performance is where you want it to be. You know, you can see very clearly how the different modes of the filter behave, and going all the way beyond the range in which the filter was designed for, you can actually see it falls all the way back, and then it starts from the beginning once again once we reach 1 gigahertz. So it has a very interesting cyclical behavior since it rotates freely 360 degrees the knob in front of the filter. So you can see how fast it can operate when we set it to a higher bandwidth and only sweep the channel that you're interested in, just to give you an idea what it looks like. So the instrument has one other minor sweeping issue that's a little bit frustrating. So first of all, I really like it when instruments have a light that show which port has the incident power. So this one doesn't have a light in the front of the unit itself, but it does show it here at the bottom. If you look very carefully, it tells you which port is the incident port where it's receiving power. So you can see right now it's jumping between port 1 and port 2. Now, even though I'm not asking for it to display anything that requires an incident power from two different ports, it's still doing both of the ports at the same time. But what is weird is that if I go under band average power, and if I go under the bandwidth here, and I change the bandwidth from 1 kilohertz to 10 kilohertz, then it simply stops doing that, and it says none down here, which means that it doesn't think it's doing any stimulus power on any of the ports, where of course it is, because it's sweeping. So it is a little bit weird, this behavior, and I wish it was a little bit more consistent, and if there was a way to set the channel to not sweep the ports that is not required, and it wouldn't somehow change through this IF bandwidth, which has nothing to do with what I'm trying to do. So you can see at 1 kilohertz, again, we're doing port 1, port 2. If I go at 100 hertz, it sweeps much slower, of course, because it's doing a much smaller IF bandwidth, but then it jumps between the two ports still. And as soon as I go to, let's say, something like, we lost that. Let's get that back here. If I go 100 kilohertz, you can see it sweeps exceptionally fast, and it doesn't even say. It probably doesn't have enough time to say which port is the stimulus. But either way, I prefer if this behavior was a little bit more consistent. Now, there's one other thing that I want to measure, and it is this NARDA phase shifter, just so we can have a complete measurement and take a look at the phase of the signal as well. This is a very good phase shifter, so you should have a very good frequency, flat frequency response, and it can phase shift, and degrees per gigahertz is written here by turning this little knob over here. You can set the phase. So let's go ahead and hook it up and see if we can do some reliable phase measurement. And here's a phase shifter connected to the instrument. I'm sorry if it's a little bit out of focus. I just want you to see the numbers there. So as you can see, the insertion loss is very good. It's fairly flat, but we can zoom in and investigate a little bit further. Let me add a marker to it. Let's put a marker somewhere around here, and let's go ahead and focus and zoom around here. So you can see that indeed we have some ripple, and that's to be expected. At higher frequencies, this phase shifter will have some ripple in its response. And I can go ahead and grab the marker and put it over here, so we can see we're at about minus 0.5 dB insertion loss, and the peaks over here minus 0.26, so about maybe 0.25 dB of ripple at the higher frequencies. But that's not really what I wanted to see. What I wanted to see was the phase. So let's go ahead and change the display format, and let's look at the phase. And of course, the phase is going to look like triangular because it's a true time delay and the phase is wrapping around. So this phase shifter is a mechanical phase shifter. So it's literally changing the distance between the two ports. So it's really a true time delay system. So let's go ahead and move this marker to, let's say, a frequency of around 4 gigahertz. Remember, this phase shifter works from 3.5 gigahertz up, and that's where those numbers actually begin to make sense. So let's go ahead and try and, let me see, what would be a good place with 4 gigahertz. Can I double click on this? No, I need to press the marker button. It would be nice if this came up when you double click that, and put 4 gigahertz in here. There it is, and this doesn't go away, it has to go away on its own. So at 4 gigahertz, we're sitting at a phase of minus 84.5 degrees. So let's go ahead and try and change this phase by exactly 10 degrees and see if that number makes sense. So let's go from minus 84, let's say, to minus 94. I'm going to go ahead and turn this, and let me see, minus 87. Can we get to minus 94? And there you go. Minus 94. Perfect. And check it out. We are sitting at 2.5. Now this is degrees per gigahertz. We're at 4 gigahertz. So 2.5 times 4, 10 degrees. It makes perfect sense. So the measurement is really, really accurate and very easy to do, of course, with this instrument. So I'm quite happy to see that. Now that we have some familiarity with it, let's start doing something a little bit more complicated. So the next item I want to look at is this antenna module. So this antenna module is intended for use with drones. It operates at 5.8 gigahertz, and the input or the output of the antenna is connected to this SMA cable, which you can then connect to a wireless transceiver to create a link to send video or data over to your drone, for example. Now the structure of this antenna is fairly interesting. It's a quad patch antenna, so it has 4 patches, and as you can see, the input comes in, splits into 2 with the power splitters into the bottom patches, and the top patches have a 180-degree phase shift between them because the feed line of the antenna at the top and the bottom are on opposite directions, and therefore the vector of the E field is in the opposite direction. You need to correct for that. If you don't do that, you get a null in the middle of the antenna. So this is actually a beamformer. It's not a phased array, but it's a beamformer, and I might do a tutorial on beamformers and phased arrays at some point, but it's an interesting structure nonetheless. Now it's actually a triple patch coupled antenna system, so that makes it even more interesting. And by that I mean that it has other patches which are coupled to each other, so it's a triple patch coupled system. Here we go. There's 2 other patches which are sandwiched, and the first patch that you put on is these circular patches, and the second one are square patches. Now this itself is quite interesting. Coupling patches together is a very common technique and can be used to either extend the bandwidth or extend the gain of the antenna depending on the distance. Now this is a 5.8 gigahertz system. Wavelength is about 5.17 centimeter, and the distance between these patches is about 0.1 lambda in this design, and the distance is determined by these little spacers which you can put on top of these little screws. So 0.1 lambda is really close, obviously, is an extreme near field, which would then classify this as E-coupled, capacitively coupled patches which re-radiate. It's, again, very common technique that is used. The dielectric in this case would be air. Now, the use of a circular patch in between two square patches itself is interesting, and it might be because of the fact that it would allow you to couple the top patch and the bottom patch, because the circular patch isn't entirely overlapping in the middle. That gives you an extra degree of freedom. But to be honest, in order to really understand exactly why these circular patches are chosen, you'd have to do a full EM simulation. Isn't very obvious. So nonetheless, I would like to measure the response of this. Now, as you can imagine, the response of it would be heavily a function of whether these patches are installed or not. If they're not installed, the response will be completely different because they are coupled in near field in such an extremely short distances. So we're going to assemble it step by step once it's connected to the instrument and see how it behaves. I think it's fairly interesting. So I have the antenna now connected to port 1 of the instrument, so we can measure S11, and here it is. Unfortunately, I can't hold it in my hand while I do this assembly, because then my hand would be in near field and of course would interfere with the antenna. Even in the Ferenczal zone, my hand will influence the antenna's response, and we can see that at the end. So let's go ahead and try and assemble this. Right now the instrument is set to S21, so I'm going to change that. Easily done. Right click, S11, and let's see how bad the response actually is. So we're looking between 4 gigahertz all the way to 6 gigahertz, and as you can see, I have a marker here at 5.8 gig, which is where this antenna is supposed to be matched, and it looks really bad. That's to be expected because the other patches are not installed yet. Another thing to note is that it looks like this antenna would actually be tuned at a slightly higher frequency than what it was designed for. So it looks like it would be tuned around 6 gigahertz. Now this is where I wish this instrument actually went to 7.5 gigahertz. There are a lot of spectrum analyzers these days that do 7.5 gigahertz band, and the primary reason for that is if you're working in the upper ISM band, you want to be able to capture some of those frequencies above your band just to see what is going on. So it's a shame that it stops at 6 gig, but nonetheless, it will do what we want to do in this experiment. So let's go ahead and put the first piece on and see what happens. So here's the first one right there. I'm going to drop it in, and let's see what happens to the return loss right there. And here is the first one. And check it out, we've already gained some improvements in the return loss, and you can see indeed I was right. At the higher frequencies we are getting even better. And there is also another mode match here, which is most likely not going to be very good for radiation, but nonetheless it is going to have a good return loss. So now I can go ahead and put a second patch and see how much that improves everything. Alright, and here is the second patch. Let's put that on there and take a look and see what happens then. There we go, and look at that, the difference is quite dramatic. As you can see, at 5.8 gigahertz, now we have a return loss of just better than 10 dB, about minus 10.8. But it does get significantly better, and it's about minus 15 at 6 gigahertz, and it looks like it might be going a little bit even lower beyond 6 gigahertz. So this is definitely not tuned at the frequency where you want it to be tuned. I'm going to tighten the screws just to make sure that the spacing is fine, and then we can see what happens as I bring my hand close to it. And there it is, everything tightened, and then you can see we got a little bit better response. And it makes sense because the spacing is exactly what it was designed to be now, with everything tightened down. And here we're almost at minus 20, so definitely not matched at the right frequency. And the other frequency where we're getting a reasonable match is at around 5 gigahertz. So having said that, let's go ahead and bring my hand closer. So if I just pick up the antenna with my hand over here and bring my hand on top of the antenna like this, then obviously the response will just be all over the place. And if I just hover my hand over it, I will be able to influence it in some interesting ways, and if I just have it at the right distance, I can create a notch, as you can see. So I hope this gives you some appreciation of how impressive it is that we have mobile devices where the antennas are exposed and people are holding them in all different kind of ways, and we still get the reception. This is an art really to create these type of antennas, and the engineers who do this are very clever, and they figure out ways how to design circuits and systems that are resilient to these changes. So now the next thing I want to do is, as you know, I'm a big fan of being able to use instruments for more than one purpose. So I want to see how good the sources that are inside this network analyzer actually work. So can I use this as a synthesizer when I set it in the CW mode Now, normally, the phase noise of the signal coming from a network analyzer isn't very critical, because you're looking at ratios and you have phase noise correlation, so they cancel out. So it's not such a big deal. But nonetheless, if this instrument has good harmonic rejection and it has good phase noise, it can operate as a 6 gigahertz synthesizer also, which would be fantastic, because then you have also a synthesizer when you have this instrument. So let's go ahead, hook it up to another spectrum analyzer and measure the performance across frequency and see if it can be used for that purpose. So while my spectrum analyzer is booting, let's go ahead and change the mode of operation of these Rohde Schwarz ZNLE6. So by that, I can go to the sweep right here, and I can change the sweep type from doing a linear frequency to a CW mode, and it also has a time mode and of course a log frequency mode. So let's go ahead to CW mode, and as soon as you do that, then you will get a fixed frequency. So here the frequency is 1 gigahertz and the stop is the number of points. So this obviously will sweep back and forth. Now, another thing I noticed, which is a little bit annoying, is that as you can see right now when the frequency is at 1 gigahertz with a bandwidth of 1 kilohertz, we are on channel 1, port 1 only, because I'm measuring S11, so port 1 should be the only port that has incident power. But if I go ahead and change the frequency, so let's go ahead and click on frequency here, and I'm going to change the frequency from 1 gigahertz, let's say, to 5 gigahertz. I'm changing nothing else, and then all of a sudden it starts doing port 1 and port 2. I'm not sure why it does that. I think it's a bug in the firmware, and hopefully this can be fixed. The reason this is a problem for CW mode is that if you want to use this as a synthesizer, then at frequencies above 4 gigahertz or so, every time this reaches the end of the screen, you would lose the signal, because then the incident power will be on port 2. I'm sure this can be easily fixed with the firmware, and hopefully they will make that change. But for our purposes, we can still use it without an issue. So let's go ahead and put the frequency back at 1 gigahertz, and my spectrum analyzer is almost ready. So it's 1 gigahertz, and I can go ahead and change the number of points to a much larger point. Let's say make it 10,000. Can I do 10,000 points? Let's see. The maximum number is 5,001, which is fine. Okay, 5,001 points will be fine. Now it's going to take quite a bit longer to get to the end, and I can also change one other parameter, which is the IF bandwidth, which is over here. And by changing the IF bandwidth to, you can see that this is a change in my spectrum analyzer's input as it is calibrating, so the return loss changes, which is interesting. So let's go change the bandwidth to 100 hertz. Now this will sweep very, very slowly, and it will interfere with us while we want to our measurement, which would be fine. Okay, great. So now that this is set up to the spectrum analyzer, let's look at the quality of the signal at 1 gigahertz. Oh, the other thing to note is that I actually have the power set to 0 dBm. Now, another limitation of this instrument is that the power can only be adjusted between 0 and -10. That's the range, because it doesn't have a mechanical attenuator built into it. It only has the electronic attenuator. So you still have a 10 dB dynamic range in the synthesizer output that you can use. It'd be nice if it had a mechanical attenuator also, but you can use an external attenuator if you need it. Normally, a range that I think is very nice for network analyzers is between -10, let's say, to -20. Between +10 and -20 is a good range. But again, this is an entry-level instrument, so some compromises have to be made. So to the spectrum analyzer. So we'll use the Keysight EXA signal analyzer to do this measurement. I have the span set between 0 hertz to 10 gigahertz. Let's go ahead and reduce the resolution bandwidth a little bit. And take a look at this 1 gigahertz signal. It's very, very clean. I'm quite impressed with how good the synthesizer is in terms of harmonics right now. And you might see a signal over here which comes and goes. That's actually from my wireless microphone. It's not from the system itself. But look at this. We have about 45 dB. Our second harmonic is about 45 dBc, which is very good. Now the question is the phase noise just as good or not? Well, we can go ahead and measure the phase noise as well. Let's change the mode here to phase noise. And it's already at 1 gigahertz. So let's go ahead and change the frequency, or the mode I should say, to a log plot. And let's measure a wider frequency span up to 100 megahertz. And there it is. Let's enable our table. There we go. So as you can see, at a 1 kilohertz offset, our phase noise is about -97 dBc per hertz, and at 1 megahertz offset is -132 dBc per hertz. This is very, very good for just a synthesizer built into a network analyzer. You can do a lot of work with this. The phase noise of the EXA is about 6 to 10 dB better, so I'm definitely measuring the phase noise of the Rohde Schwarz network analyzer, but I'm really happy with this. It means that you can use this in your design to doing some other measurements and some other testing. So it's quite nice. In fact, I think here at 1 megahertz, we might be so close to the noise floor of the instrument. I'm not sure if this is even very accurate. It might be a little bit better than that. But either way, I'm really happy with it. So let's go back to spectrum analyzer and let's take a look and see if the harmonics remain just as good at higher frequencies. So let me go ahead and change the frequency. I'm going to set the frequency from 1 gigahertz, let's say, to 2 gigahertz. And here it is at 2 gigahertz. Yep, it's good. You still have about 40 dB of rejection over there, 40 dB of harmonic rejection, which is also pretty good. By the way, the power is also very accurate. The minus 2.7 dBm you see is because of the loss of the cable. So when you set it to 0 dBm, you really are getting 0 dBm. And I'll demonstrate that. I'll change the power from 0 to minus 10. So I can go ahead and change that quickly here for you. So I'm going to go ahead and change it to minus 10 dBm. And check it out. You can see that it went down by exactly 10 dB. So it's very accurate. And all the other harmonics went also down even more so. So this linearity seems to be coming from their final output drivers on their synthesizer. So it's really quite good. Let me go ahead and change the frequency all the way to the highest frequency here. Let's go to 6 gigahertz. And there's your 6 gigahertz, and there it is. It looks good. And of course, it's going to have lower amplitude there. So it's minus 17. I have a lot of loss in this cable. This cable is not very good at 6 gigahertz. But I am very happy with it. I think this is an excellent built-in synthesizer, which you can use for other purposes. And for completeness, here I have the output of the network analyzer connected to a power sensor. And the power sensor is connected to my power meter, set to 6 gigahertz and 0 dBm. And check it out. As I said, it really puts out 0 dBm across the entire band within less than 0.3 dBm. So it's very good. It's both harmonics are good, phase noise is good, output power is accurate. Really couldn't ask for anything more. And I would also like to take a quick look at the mixed mode S-parameter measurement capability of the instrument. As I said, you can do a common mode calibration. This is exactly what I've done here. And in common mode calibration, the instrument can compute common mode versus differential S-parameters to give you mixed mode S-parameters, so you don't have to use an external transformer, for instance. This is very useful and of course can be done because these are linear systems. So what I've done is I've connected the two ports of the network analyzer to a resistive power splitter or power combiner, which looks like this. So these guys is a purely resistive component. So the two ports, port 1 and port 2, are connected to this. The third port is connected to a microwave tuner. And here it is. This is a mechanical tuner. You can change the distance for the stub. You can change the resistance of it. So it has full flexibility from that point of view. And the end of the tuner is terminated into 50 ohms. So by adjusting the tuner, I can change the impedance seen at the third port of the power combiner. Now, the differential and common mode response of this are going to be very different, and I want to investigate that. This is a good lesson for people using resistive combiners in microwave applications and how important it is to control the impedance of the third port if you have differential and common mode stimulus signals. So let's go ahead and take a look at the screen and see how it changes. And here's the screen of the instrument. So on the left, I have differential S11, and on the right, I have common mode S11. So this is SDD1, this is SCC1. The instrument can also plot mixes between differential and common mode, but for our purposes, this is what we want to look at. So I'm going to go ahead and change the tuner and have your eye out on the two S parameters and see which of them is influenced by changing the impedance on the third port of the power combiner. And here we go. I'm beginning to change it, and have your eye out on the two S parameters. And if you pay close attention, you can see that as I change the tuner, the common mode impedance is going to be vastly different than the differential impedance. And this makes sense if you think about the equivalent circuit inside the resistive divider. With a differential stimulus, you have a virtual ground in the middle of the resistors, and therefore the impedance after the resistor is not observed. But in common mode, that impedance matters, and in fact shows up very well on the Smith chart. You can see by changing that impedance away from 50 ohms, we can create quite a mess on the Smith chart as the impedance goes all over the place. So this is a very good and useful feature. I'm very happy this is included, because otherwise you would have to use an external transformer, and all the imperfections and issues with that will be on top of your signal. You'd have to de-embed that, and this is really quite convenient. As you can see, we can very quickly configure the instrument and perform differential and common mode measurements with ease. So it's a great feature to have. So for our last experiment, I want to push the dynamic range limitations of the Rohde Schwarz network analyzer, and I want to see how well it performs in terms of resolution and accuracy with very small signal powers. So how can that be accomplished? Well, there's different ways to do this, but what I'm going to do is use a mechanical attenuator, which is electronically controllable. And this would allow us to look at if the network analyzer is able to resolve very small changes in attenuation across its dynamic range. So here on the left, I have an Arduino. The Arduino is controlling an I2C I/O expander. So this I/O expander has 16 ports, and those 16 ports go into a series of H-bridge drivers which are able to drive the mechanical attenuator. These LEDs that you see here are showing you the current state of the attenuator, so it's running through all the different attenuations at the moment. And the attenuator actually has only 10 bits, and that means it has 1023 states. And if you look at the attenuator over here, this is a very good model itself, and 10-bit attenuation, electronically controllable, that's really good. And because it's mechanical, its repeatability is excellent, its linearity is extremely high, and for the powers we are using, it's not going to suffer any thermal drift or anything like that. And so we're going to use that to basically test the network analyzer. The smallest step this attenuator can take is 0.1 dB, and the largest is 32 dB, and it's somewhat binary weighted. A little bit change here in the middle of its range, but it's generally binary weighted. Now, for a binary weighted attenuator like this, the maximum attenuation is about 64 dB or so. That's actually not enough really to push the dynamic range of the network analyzer. So I also have a mechanical attenuator here, which is controlled manually. You can adjust it, and it can go from 0 to 70 dB. So in combination, you have a huge range of attenuation that you can apply. So we're going to take a look at that combination. So right now it's running, and the port 1 of the network analyzer is connected to port 1 of the attenuator, which then is cascaded with the other one and then returns to port 2. So we should be able to do this. Now, I also want to make this measurement very precise and time predictable, so I'm going to configure the network analyzer with an external trigger. The trigger itself is also provided by the Arduino itself and is using this cable right here. So this goes to the back of the instrument to the external trigger port, and we can use that to trigger the unit. There is really nothing else going on, some power supply coming from the outside to power all the I/O expander and the high voltage H-bridge drivers to give the 12 volt to the attenuator, and that's our setup. Now, the reason I'm using everything here kind of electronic without touching it is because you don't want to move the cables. You don't want to touch this as it is running. You don't want to move it around. So that's why everything's kind of sitting still. And to further protect that, we're going to use the LXI interface of the network analyzer, and we're going to do this on the computer. And at the same time, you're going to see how well the computer interface works and how well you can do a remote control of the network analyzer. I think this is a pretty cool experiment. So let's go ahead and take a look how it behaves. So let's go ahead and use the LXI interface from the instrument. Now, Rohde Schwarz has one of the best remote interfaces in the industry. They're fast, responsive, and they work really, really well across a wide range of their instruments. I've already shown it for their oscilloscope, so now we're looking at the network analyzer here. All the front panel controls are available here at the bottom, and you get a live view of the screen. And interestingly, everything that you do on this screen is mirrored directly on the network analyzer. So this mouse actually that I'm using my computer for is mirrored on the instrument too. So now we can go ahead and see if we can measure this attenuator and see if all the steps are there, if the steps are correct, and how it behaves across the wide dynamic range. So let's go ahead and give it a try. It should be pretty straightforward. Let me just show you how I've set it up. So I've set the sweep a number of points to 2500. The sweep type is in CW mode, and the frequency at 1 GHz, which is a frequency of the attenuator where it is supposed to operate at its best performance. And then a few other things I can do here. For example, on the trigger, I have it set to external trigger, and the trigger level when it hits a high level. So I have a signal coming in, which will then trigger per point. You can see I am sequencing it per point. So I can go ahead and let go of the reset on my instrument, and it should start sweeping. So here we go. There we go. And as you can see, there it is. It's beginning to sweep from the top. So it's going to take 2 measurements or 3 measurements per attenuation level. So right now, obviously, we're looking at it from very, very far away. So we can see that the attenuation is slowly increasing. And the very, very first value at the top left corner there is our starting point. So let's go ahead and zoom there and see what it looks like. Here we go. And there it is. Check it out. These artifact lines that you see here, if they're visible to you, and they only show up on the computer. They're actually not on the screen. So there must be something with the drawing of the graphics on my browser that is causing that. But look how nice it looks. These are our individual steps. Now, if you look closely, they're fairly evenly spaced out. So let's go ahead and measure 2 of them. So I should be able to put a marker here. So here's our first marker. Let's put the marker somewhere arbitrarily, let's say over here. And I can go under the marker menu and I can make this a delta marker and put the other one at the next level over here. And we can see that our step is 0.126 dB, very close to 0.1 dB that it's supposed to be. Let's measure the next one, put that one over here, and put this one right next to it. And you can see this one is 0.1074. So these attenuators are not exactly the same step each time. And that makes sense because there is some repeatability limitation. Now, this is not because of the instrument. In fact, the network analyzer is revealing the imperfections of the attenuator. So we can go further down. And you can see it continues to go forward. This jump that you see going up here has to do with the fact that the attenuator isn't exactly binary weighted, and there is a transition where we have half a dB of step. So this step actually should be half a dB. So we can go ahead and measure that. Let me see what is the easiest way to grab these markers. So let's put the marker over here, and let's put this marker over here, and this step should be half a dB, and you can see at the top right corner is 0.5429. So again, very close. Now, this is at a reasonably low loss. This is at -5 dB loss. So these steps are going to be very clear. If I go ahead and go back to zoom, you can see it's slowly working its way down. Now we are at a 10 Hz IF bandwidth, so the steps take about 200 milliseconds, and I have to give time for the attenuator to settle and make more than one measurement. So we are sweeping very slowly and moving along. Now I can also go and look over here, look at some of the newer points and see the transition. You can see right over here we see an imperfection. So let's take a look at that imperfection a little bit closer. So it looks to me like this step is not the same as the previous steps. But we can verify that again by going under the marker. Let me turn all the markers off here and create a new one and put it right there. That's exactly what I wanted, and do a delta. So let's compare the step after, which is 0.1164 dB, with the step before. If I can grab the marker again, and the step before is 0.15. So indeed there is a difference between this step, and if you look carefully, we can actually see that this behavior repeats itself. Let me zoom in a little bit further. There it is. You can see that point is again not working very well. You see how nicely this is going down, and on the next cycle there's a jump there. That's because the attenuator's repeatability is not very good. Every time it hits this particular attenuator, sometimes it hits the right value like it did in the previous cycle, but in the next cycle it doesn't hit the right value. And we are looking at very small changes, and of course the network analyzer is reproducing that really well. So we can tell, even looking at it from this distance here, that there is a problem with this. You can see it is not okay here, it's okay here, it's kind of okay here. We can go forward again. You can see again that the step is a little bit different on this cycle, and we can continue this over and over again and check to see if our attenuator is actually behaving correctly. This is a very useful parameter to be able to take a look at. Of course, this instrument is doing very well. So let's go ahead and increase the attenuation by using the mechanical attenuator and push ourselves well down into a much higher attenuations and see what happens. So I'm going to give us 30 dB additional attenuation. So now we're looking and sitting around -50 dB of loss. Remember, this is getting significantly more difficult in terms of the performance of the analyzer. Now here, this is the settling time of the attenuator mechanically as I switched it, so we ignore that part, and we zoom over here and look, we see very nicely again the steps, even though we are at a 50 dB loss and the network analyzer has no problem reproducing it. Even the bad step, you can catch it again even at this attenuation. So this is exactly the same problem we were looking at before. I can measure it even here at this attenuation. You can put a marker over here and put the delta marker, and put that delta marker over here and check it out, 0.166, which was the problem we were seeing before, but the previous step was good. And check it out, the previous step is good. This is pretty impressive. This is a fairly high loss system, and we're only putting 0 dBm from the network analyzer. So to be able to catch this at such an attenuation is very nice. So let's go ahead and zoom back out again and look at the latest points that are being measured. Here we go. We can see the steps. Here we go. Here's the bad step once again, still visible. And let's go and add some more attenuation. So I'm going to take it to 60 dB. So now it's really pushing the dynamic range in terms of accuracy. Remember, this can measure well below where we are now, but we're trying to resolve 0.1 dB steps. So that's where the difficulty is, and I'll show you as it works its way out. It's going to continue to go down, and these lines are going to be well visible and lower powers, but of course I'm interested in capturing tiny changes. So let's go ahead and zoom over here, and here's the steps. You can see that we're beginning to lose some of the accuracy of the steps, but the trend is really still visible. For example, we know this jump should be about 0.5 dB, and we verified that it is 0.5 dB, and there you go. Here's a mistake again from the attenuator, as you can see. So clearly that problem is still well visible here. So let's go ahead and look at some of these. Let's say this jump here, which we know what it's supposed to be. Let's grab the marker. I wish there was an easy way to bring the marker forward without having to create it again. So let's put the marker here, put the delta marker, put that one there, 0.57. So we are still catching tiny changes in loss at an attenuation of 86.1 dB. So this huge dynamic range and the repeatability of the instrument is what is being tested here, and we have no problem catching that. So I'm quite happy with that. Let's go ahead and zoom back out. And there you go. We can now push the reference point to -30, so we're reaching even lower values. Let's actually put it to -50. I can add 10 more dB attenuation. There we go. So now we're at -100, right? So at -100 dB of loss, we can go ahead and zoom here. And it's going to be more difficult, as you can see. Yep, it's now much harder for the instrument to give us an accurate representation of each individual step. There's just too much noise. Now, a few other things to note. I have no averaging here. The only thing I have is a 10 Hz bandwidth. I'm not using any of the math functions which would allow us to make multiple measurements and average them out. None of those is being used here. So this itself is going to limit, of course, the performance. And here's that jump again. So if I look at it from far away, I can still see the trend. If you look carefully, let me get rid of these markers so we can have a clear view. This line over here with the individual jumps is roughly being represented here. So we are now at -100, -110 dB roughly. So I'm going to wait a little bit longer and let this play out and continue, and then see if we can see the trend. At what point do we no longer see the line? And here now some more time has passed, and as you can clearly see, the trend continues until about 120 dB down, and even up to -130 dB down, you can clearly see that we are linearly reducing, increasing the attenuation. Now again, I want to emphasize that this is done without averaging. This is only an IF bandwidth of 10 Hz. If you were to average every measurement several times, a significant portion of this noise will be eliminated. So without doing that, to get such a large dynamic range is really quite impressive for what is an economy instrument, an introductory instrument. So I'm very happy to see that. So you can detect flaws and look at very deep filter notches and rejections, out of band rejections from microwave components quite easily with this. So it's very nice, and the repeatability is excellent, of course. And right now you can see this wrapped around because we hit the 2500 points. So we're coming around and we're essentially sitting at the noise floor of the instrument around this line here is -130 dB down. So yeah, it works really well. And if I were to, for example, go and change the attenuation back to, let's say 0, we would jump somewhere up and continue our measurement once again. There you go, there we are over here. So now I can zoom back here. We're at -67. So it has no problem, of course. Very repeatable, excellent performance. So no complaints from that point of view. And there are many other features which I simply could not go over. The instrument has an extensive set of functions you can perform on traces. You can add and remove traces and have multiple traces, smooth them, average them, export them and import them, and look at them in different formats, which is of course very helpful. And I showed you some of the different formats it supports, but it also can give you measured S-parameters in the raw format. So you can look at Z parameters, Y parameters, ratios, as well as stability factors, both mu and K factors. So you can look at it for active components. It has a very nice set of embedding and de-embedding functions. So adding delay, adding fixtures, removing fixtures, accounting for ground loops, differential, matching, balanced measurements, all of that. Some of those we already took a look at. Here's a block diagram for the embedding and embedding functions. Again, these are features which are very useful. Normally, you would have to do these outside of the instrument, so you'd have to write your own functions, but having some of this built into the unit is extremely helpful. But if I wanted to show you all the features and everything this unit can do, it would take another several hours. But I hope that I gave you a good impression of what it can do And as I said earlier on, I think Rohde Schwarz is competing on feature set on this economy instrument, which is great because that means you get essentially more for the money you would be paying for these anyway. I know that these are sometimes a little bit more expensive than some of my viewers can afford, but remember, in the industry, this is not an expensive unit. Something less than $20,000 with the features it has, a dynamic range and performance from Rohde Schwarz, is not expensive. So having said that, I hope you enjoyed all the different features here. I think it's a really nice unit. And there you have it. I hope that you enjoyed this product review. I certainly really enjoyed making it. I'm quite happy with this instrument, and I'm sure it's going to show up in other videos in the future. Now, if you want to support the channel, there are several ways to do it. You can obviously subscribe to it and leave a comment and engage with the channel. This allows the algorithms to show the channel more often to other people so that everyone can benefit from the videos. There are a lot of other videos that I intend to do. I've just been very busy quite lately, but I'm going to get to it as soon as possible. And if you want to support it on Patreon, you can also do that. Every money that goes into Patreon goes back into the lab for purchasing broken equipment and components, and of course video production. And another way you can help is to just let the vendors know, like Rohde Schwarz, Tektronix, Keithley, and whoever, that you watch these videos and the reviews are beneficial to you and they help you make decisions on the purchases. I get no benefit from the components or instruments sold by any vendor. All the links from my channel that go to the vendor sites, they're all untracked and they're just direct links. And this is just so that the vendors know that these videos are valuable to you. It gives me a good relationship with them so that I can get other instruments to review for you guys. So I hope you enjoy this. I'll see you in the comment section.